the gold standard parameter that we calculate for EEG, but if you look at what people are beginning to talk about when it comes to brain activation and neuroimaging, as we saw in some of the earlier lectures, while localized regions of activity are very important, and it's very important to be able to determine those, the brain probably doesn't work as little isolated islands of local activity. In fact, it works as connected networks distributed throughout the brain, connected by white matter tracts, and often working in synchrony, not just in one local region, but spread out over a wide area. So there's been a move in recent years to look at this connectivity, and there are a number of techniques, some stolen from communications, some taken from graph theory and other mathematical models of connectivity and pathways, and others that have sprung up unique to the EEG. So the first of these is EEG coherence. This has probably been around the longest as a connectivity measure. It's a method used to determine connectivity between brain regions, and basically what it is it's like a cross spectrum between two different channels. So what you're really looking for is commonality in the spectrum. It's important to keep in mind that coherence between two channels doesn't necessarily correlate with coherence between two brain regions, because remember, your channels receive a superposition of brain activity from several sources. So one kind of false postulate that people can make is if they see a high level of coherence, it's important to rule out, for example, that you don't have a lot of common mode noise or common mode signal. If you've got a lot of common mode signal, then you could have sort of this false coherence that really just represents that maybe you haven't referenced well, or maybe you have not removed common artifacts like the heartbeat, or common artifacts that would be very coherent with each other but don't necessarily represent coherence between brain activity. So that's just sort of a disclaimer about coherence. Okay, having said that, here's just an example mathematically of what coherence is, and I've always had a little trouble getting my head around this cross-spectrum idea or this cross-spectral density idea. It's easier for me to think about cross-correlation, because remember, spectral density is just the integral of the correlation function. So if we wanted the power spectrum of a given signal, we would integrate its autocorrelation function. If we want the cross-spectral density between two given signals, we can integrate their cross-correlation function and take its Fourier transform. So it's the integral, but it's the Fourier transform. So to get from correlation to spectrum, we take the Fourier transform of the correlation function. So obviously we have channel X and channel Y, and we want the cross-spectral density between those two. We could take the cross-correlation function, find its Fourier transform, and that would give us the cross-spectral density. So now coherence is defined as the magnitude of the cross-spectral density over this normalizing factor that's the spectral density of, or the spectrum of channel X times the spectrum of channel Y taking the square root. So this is a kind of a normalizing factor. This is the cross spectrum. Now obviously if X and Y are the same, exactly the same signal, what does this turn out to be? This turns out to be 1. So the maximum value you can ever have for coherence would be 1. And a coherence close to 1 means that you have nearly the same signal on the two channels. Now in EEG, there have been, throughout the last probably 15 years, maybe 20 years, there have been some pivotal papers that defined common or relevant coherence channel pairs. Especially early on, there were lots of folks who did this. So here is a figure that shows, excuse me, given a 16-channel EEG, which is how some of the early coherence channel pairs were defined. Given a 16-channel EEG, this shows some different common coherence pairs. Now, why were these selected? These were selected because there are known fiber tracts in the brain that go across these regions. So we know, for example, that there is a superior longitudinal fasciculus tract that goes from the frontal lobe to the parietal, and some of these channel coherence pairs were chosen to represent connectivity via that white matter tract. So here we have illustrated far coherence, anterior coherence, which is the frontal part of the brain, posterior coherence, which would be coherence between channel pairs in the posterior or back part of the brain. Another author defined coherence in a very similar way, this posterior to anterior and anterior to posterior, one being directed from back to front, the other being directed from front to back. And here are the corresponding channel pairs according to the 1020 electrode configuration. So when you're calculating coherence, you definitely follow the 1020 electrode configuration. Now, so coherence is for channel pairs. Let's talk about magnitude of data again. If you have 16 channels of data, and usually coherence comes out as a function of frequency, and then typically an average coherence is taken either across a frequency band or across some predefined range. So in the early days, people basically would take 4 Hertz windows, 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20, and so on, and calculate a coherence number for each bin. Now people tend to do it corresponding to the relevant EEG frequency bands. But if you think about that, we can come back up and look at this chart again. These are just some potential channel pairs. So if you did every channel with every other channel, which is what some of the more modern methods are doing, because now people are starting to look at interhemispheric coherence, people are starting to look at graph theory models and using coherence as a way to represent the strength of connection in a graph. In that case, people take every channel with every other channel often, and you can just imagine that the number of data points gets much higher than just the number of channels. So even for a 16-channel system, you can do the math and figure out how many channel pairs you would have out of that, and then for each channel pair you're going to have a coherence number for whatever frequency band. So once again, this becomes just a huge, almost unmanageable amount of data. So another parameter that people are looking at, and this is a more recent development, is the generalized magnitude squared coherence. In this case, you would take all of these coherence values and form a matrix. And from the matrix, you would look at the maximum eigenvalue, and that would then be used in your generalized magnitude squared coherence. Generalized magnitude squared coherence is believed to be more of a global measure of coherence. So rather than talking about a specific, say like frontal to parietal coherence, you're talking about the state of coherence in the whole brain. So it's a whole brain kind of measure. And here is just a representation in the mathematics. Your matrix, basically x1 and x2 would represent or x1, x1 would represent self-coherence. So coherence of the channel with itself. X1, xm represents channel 1 and channel m. So you have m channels here, and you're finding basically a matrix that represents the coherence of each channel pair, with m being the number of channels, and then you can see how the general magnitude squared coherence is calculated. So lambda max is going to be the largest eigenvalue that comes out of that matrix. So once again, the nice thing about this is you do come out with one number that sort of gives an overall whole brain coherence. The not so nice thing is it's kind of hard to interpret, and a lot of times connectivity problems that show up in either people with diseases or disorders are localized and not general, but not always. So it's just another number to work with.